Hi, I'm Professor Angela Rasmussen from the Department of Electrical and Computer Engineering at the University of Utah. Today I wanted to go over another example of Bode plots using the approximation technique that we went over when we have multiple poles at the origin. So this was one of those other cases. So here we have the equation, the transfer function in terms of S, and we need to first get it into standard form. So when we change it into standard form, we're going to take out this 100. We're going to multiply it by the 100 that's already out there. We're going to also have to take out this 10, so I'm going to multiply that out in front. And now each of these quantities will look like this. So we have S over 100 plus 1, S over 10 plus 1. And on the bottom, we have to take out this 10K and multiply it on the bottom. And so that gives us the quantity of S over 10K plus 1. So the term here, this S squared, is not an S some number plus 1. So this is how we determine when we have a pole or a zero at the origin, is it looks like this. So there will be a single S by itself. So in this case, there's 2 because it's S squared. So there's 2 of the effects that happen when you have, in this case, it being on the bottom, meaning that it's a pole, 2 poles at the origin. So this determines that there's 2 poles at the origin. So the next step, we would want to determine the order of poles and zeros. So I always find the lowest value. And we have a 100 and a 10 for our zeros. And we also have this 10K for our pole. So for our poles and zeros, our lowest value is 10. And then we have a 100. And then we go to 10K. And so from here, I circle. So at 10K, I have a pole, and at 10 and 100, I have zeros. So before, when we saw the standard form, we did not have any poles or zeros at the origin. So we just took 20 log of the number out in front. But when we have a pole or zero at the origin, that means that there's going to always be a slope through wherever we start, because we can't start at 0. So in this case, having 2 poles means that we double that effect. Each pole has a minus 20 dB per decade effect, and so we have a slope of minus 40 dB. We need to know, where does that intersect our graph? If we have our graph at 0.1 and we started there, we want to find what that value is. So we're going to take the magnitude of this at 0.1. So at omega equals 0.1, we take the whole magnitude, and we're going to take 20 log of that, base 10. So remember, you're going to square root the number out in front, and then you square it again because there's no imaginary portion. Then you're going to multiply that by the square root and substitute in j omega, with omega being the 0.1. So we'll square that, plus 1 squared, and so on. So we're going to have 0.1 over 10 squared plus 1 squared, didn't quite fit, all over the square root of 10K squared Sorry, this wasn't squared up here. So it should be just the numbers, all these numbers squared, and then take the square root of them. So that's 10K squared and the square root of it. And then you're also going to take the square root of 0.1 squared. So if it is just one pole at the origin, it would be 0.1 squared and then the square root. But since we have two of these, we have to square that whole thing. And then multiplied by, again, 0.1 over 10K squared plus 1 squared. And we multiply this out, and we find that at omega equals 0.1, we end up with 60 dB. So this gives us this point of 60 dB. We know that it's now going to be a slope through there of minus 40 dB because each pole at the origin has a minus 20 dB per decade effect. So we don't have any change until the 10, so it's going to go down by 40 each decade. So between 0.1 to 1, which is 1 decade, it's going to go down by minus 40. So from 60 to minus 40, it gives me 20 dB at 1. And then I'll get a minus 20 dB. 20 dB minus 40 gives me minus 20 at 10. And so my slope goes down until 10. At 10, I have an addition of plus 20 dB to that. So this slope is minus 40 dB per decade. So I'm going to add on to that minus 40. I'm going to add on now a plus 20, which gives me an equivalent of plus 20, or I mean a minus 20 dB per decade. So between 10 and 100, I go down again by minus 20, so I go down to minus 40. And then here I have minus 20, and now I'm going to add on another effect from that 100, which will be another plus 20, which gives me a 0. So it's then going to be 0 until I reach 10K. At 10K, it's a pole, so I go down again by minus 20 dB per decade. So this will now be minus 20 dB per decade, and that will continue on. So if I want to find at 100K what the value would be, I would have at 100K, that's one more decade after this, so I was at minus 40, and I would subtract off minus 20, so at 100, I'm going to see that minus 60. So this would be a minus 60 dB. And so on, I could find out at any interval after that the value. So this completes that magnitude plot, and it has this form. So the phase plot I want to find next. So for the phase, I again go back to my standard form equation. I again see that I don't have any negative value, but I have two poles at the origin. Each pole contributes a minus 90 degree effect. So for two of them, I'm going to get minus 80 degree change. So I am going to start my graph at this minus 180 here. So I'm going to circle again. I had 10 and 100 were zeros, and 10K was my pole. So now I want to mark the regions. So 1 decade before and 1 decade after. So this goes to 100. I'm going to have a change from this one of minus 45 degrees slope per decade. For the zeros, again, go 1 decade before to 1 decade after. And I'm going to have a plus 45 degrees slope per decade change here for the 100. And for the 10, it will be 1 to 100. And then I'm going to add the overlaps in between each of them. So this overlap gives me plus 90 degrees slope per decade because I add the plus 45 from this one and the plus 45 from that one. And then I don't have any other areas that are overlapping. So I go back to my graph. I don't have any effect in here till I reach 1. So at 1, I have a plus 45 degree per decade change. So I'm going to change from 1 to 10, 1 decade. I'm going to go from minus 180 plus 45 gives me minus 135. And then I have a 90-degree change from 10 to 100. So adding on a minus 135 plus 90, I am going to get a plus 45. Oh, I mean minus 45. So minus 45. And then at here I'm already at plus 45 and I have an additional plus 45, so I'm going to go to 0. And then I have a negative 45 between 1 and 1K. So I'm going to go back down to negative 45. And then I'm also going to go back down another negative 45 to be at negative 90 for 100K. And then I have no more effect, so I'm going to stay at that negative 90 degrees basically forever after that. So at 100K I'm at minus 90. At 1 million I'll be at minus 90 degrees too. So this concludes the solution. Thank you for watching.